So in the last lecture, we started with acid dissociation constant, but we were unable to continue. We will be trying to do a short recap from where we started in the acid dissociation constant, and we will be continuing from there. So the term acid dissociation constant brings its way from the term the equilibrium constant Kc. So we will be following up the strategy of Kc in forming the equation. But before that, what is the what is actually acid dissociation constant? The name itself, it suggests what it is. It actually like refers to, we have, let's say, an acid. That acid, when it dissolves in water or when it is placed in water, it dissociates up to a certain extent. So here it is dissociating up to a certain extent. That means there is a irreversible reaction. For let's say there actually are equilibrium establishes. For a certain portion, the reaction occurs, it breaks down, forming the hydrogen atom and the other part of the ion. Sorry, it shouldn't be OH minus. It's just which ion there is going to be, that should be placed here. If it was let's say HCl, then A minus is going to be replaced by Cl. Let's say for an example. So that's how it is. And since an equilibrium is being formed, that means there is a constant term which is going to be established here. That constant term is actually defining the rate at which the forward reaction is happening, at the same time the backward reaction is happening. Meaning the proportion, let's say the forward reaction or the production of H plus and A minus ion from this HA is certain value, let's say x mole per dm cube per second, let's say. And the term like the reversible reaction, it has a rate of, let's say, y mole per dm cube per second. This is actually meaning, let's say, x mole per dm cube. That means, let's say, this much of x mole per dm cube of HA is dissociating and forming the H plus and A minus in the forward reaction. At the same time, y mole per dm cube per second means y mole per dm cube of HA is being formed per second. Now, if we try to find out the ratio between them, y divided by x, or let's say x divided by y, we should get a value which is the constant that defines that there is a constant. Like there have that rate, that this rate x and y, their ratio remains same in equilibrium. So that's actually that constant term. And for acid dissociation constant, the term we can define it as Ka. Instead of Kc, we will be writing A because it's an acid. So Ka equals to, in simple terms, as we have written earlier in Kc, we will be writing the product in the numerator, in the top most part, and in the denominator, we'll be writing the reactant. So the product is what? The concentration of H plus. So we'll be writing the value of concentration of H plus, multiplying it with the concentration of the other ion which is present, and dividing it by the concentration of HA, which is the acid. Now, this is actually this is more towards the term which, like this concept, this term acid dissociation constant, is more relevant towards those which are weak acids. For example, ethanoic acid. So let's take ethanoic acid as an example, CH3COOH. Now, when it dissociates, or when it dissolves or breaks down in water, what happens? When it is breaking down in water, this is trying to form H3O minus aqueous plus H3O plus hydroxyl ion. This is the same thing as writing just simply H plus and H2O. So I'm just writing H3O plus together. So this is the hydrogenium ion, or we can say H plus ion. Now this is the dissociation part. Now if we break down it further, CH3COOH, as I was writing in terms of water. So let's say here we have water, and on the right hand side, we also have breaking down the hydrogenium ion, which is H2O plus H plus. So we can simply just cancel up water, and we'll be left out with simply CH3 COOH, breaking down to form CH3 COO minus plus H plus. Now over here, if we try to write the acid dissociation constant equation should be what? The concentration of H plus in the numerator, multiply it with the concentration of CH3 COO minus, and in the denominator we'll be getting CH3 COOH, the concentration of the acid. Now, in the previous lecture, I have mentioned we cannot simply, if we want to calculate the pH value of this solution, let's say, or if of this acid, in simple term, we cannot actually simply take the logarithmic function of H plus, just directly applying the concentration of H plus over here. Let's say we are given the concentration of CH3COOH 1 mole per dm cube. So we might think by doing molar ratio, we can simply find that this is 1 mole and this is 1 mole. So the acid, the ethanoic acid, is to hydrogen ion. The molar ratio is 1:1. So we can simply say the concentration of hydrogen ion is also 1. And simply we can try to place it over here. But there is a catch here. There is a catch. Now we are going to come to that catch. Like, what is actually the problem we are facing, and what is the difficulty we are facing, which is actually preventing us from using simply the molar ratio, simple molar ratio. The thing is, we know already water itself it is self-ionization. It is self-ionizing. So it undergoes self-ionization, which we did in the first lecture of the ionic equilibrium, which is it breaks down itself underwater, with itself, so forming H plus plus OH minus. That means it itself forms an H plus ion. Now, if we think of ethanoic acid as well, this is also forming H plus ion over here. So if this is also forming H plus ion and water is also forming H plus ion, then whose ion we are going to consider? If we are going to consider both of them, then we should be getting an error, because we should only find the H plus, in order to find the pH value of the acid, whose concentration we need? The acid's concentration of H plus. But here we have the concentration of H plus from water as well as the concentration from ethanoic acid. So the first assumption we need to make is we are going to assume the hydrogen ion concentration we are getting or we will be getting does not come from H2O. We know that's not true, but we have to assume that in order to do the calculation, in order to have the calculation possible, we have to assume that. So that means the only H plus ion is being produced is from what? Ethanoic acid. So that's the only source for the H plus ion. No water will be ionized. That's the assumption we are making in order to have a possible calculation. The second assumption we can say is that in equilibrium, the concentration of CH3COOH should be equals to the concentration of CH3COOH initially. So the initial concentration of CH3COOH should be equivalent to that in equilibrium CH3COOH. Now, this might be confusing, but try to think it in this way. If this CH3COOH does not break, then how will the H plus ion be produced? That means in order to break this, certain portion of CH3COOH will be getting rid of. So the value of CH3COOH is going to be decreased. Think it in normal terms. Let's say you have a piece of cake. In order to get a slice, you have to cut it and take a portion from it. That will make what? The actual amount of cake will be reduced. But the thing is here, we have to, in order to do the calculation, we have to assume that even after cutting the piece of cake and the initial cake before cutting the piece, their size are identical or almost same, so that the calculation could be made. So that's another assumption. So these are the two assumptions. If that's the case, then let's get back to the equation, which was Ka equals to CH3 COO minus H plus divided by CH3 COOH. Now, as we have mentioned, the concentration of CH3OOH in equilibrium and initially will be same. So, if that's the case, then okay. Before writing that, let's do one thing, which is we can try to write the equation and make sense of this. Like in terms of saying equation, like just by saying the equation, it will be a bit hectic. So writing the actual dissociation equation is C00 minus. Now, since at equilibrium the concentration of CH3 COOH are equal, that means this portion should be unchanged, or this portion should be considered. Now, try to look at the right side of the equation. What do we see? The mole ratio of these products are constant, isn't it? Like we can simply do the mole ratio of one of the side. Why? Let's say, how do I explain? Even if like the piece of the cake is, let's say, cut, and from that piece of cake, if we divide it into 50-50 portion, obviously, let's say if we divide it into two different people, they each are going to get half of that piece, isn't it? That's another part. Like we're considering the initial and the final piece, the final cake have the same amount. But think of this: the portion which has been like cut from the whole cake, if we divide it into like two people in equal amount, what do we have? Like have then two equal portion of the slices. That means this H plus and this CHTC double minus, we can actually like consider that they are in like equal molar ratio because they are in the same side. So molar ratio on the same side components, that's logical. We don't need to like we assume in terms of different side of the equation. We assumed what? We assumed this was equal, like this was like as like the initial and the equilibrium, like they were equal, and we assume that H plus is only contributed from CHTC double OH. But on the right hand side, we didn't assume anything like in terms of these two, their relation, like we didn't assume anything. Simply we can consider that the two are equally in molar ratio. That means we can say if they are equal in molar ratio, their concentrations are same. If they have 1:1 molar ratio, their concentration will be same. If H plus is x mole per dm cube, then that should be also x mole per dm cube. Then what can we say? The concentration of H plus is equal to CHTC double O minus, isn't it? We can say that. If that's the case, then if the concentration of H plus is, let's say, x, we can say concentration of CHTC double O minus is also x. So in place of just writing CHTC double O minus, we can replace it with H plus in the actual equation. HCC double O minus and H plus if they have the equal amount of concentration. So in this Ka equals to H plus and CH3 C double O minus in the denominator, you can simply replace this term with what? H plus, because we have just seen their molar ratio is equal. So writing that, that's fine. Why? Like consider it in this way. If H plus is X and CHTC double minus, they have like equal molar ratio, we can also write CHTC double minus X. So in like if we simply place the values in their respective position, we will get what? In terms of H plus, we will get X. multiplied with the concentration of CH2COO minus, which would have been also X, and we know X is also equal to like H. X is equivalent to H plus. So that's what I was writing, like in terms of the equation, we can write H plus divided by CH3 COOH. Now see, our one of the variable has been removed, CH3 COO minus. Like, we don't need to deal with that anymore. So if H plus and H plus is here, you can simply form an equation to find the value of H plus. Let's simplify this first. This could also be written as H plus what? Square plus 2H plus multiplied with each other. CH3 COOH. Now we can simply write it what? We can like make subject of H plus and taking all of the other materials on the other side, which is CH3COOH. We should be getting now H plus, concentration of H plus, which is root over or square root of Ka times CH3COOH. Now did you get it? Like why we were unable to like find the actual pH value from the like, simple molar ratio? Because H plus's concentration is now actually this. This right hand side is the concentration of H plus. This is how we need to find the value of H plus in terms of like weak acids. If we are able to like find H plus now, then we will be able to like simply do the simple logarithm, negative logarithm of H plus, and now this is fine. Now simply we can place this concentration value over here, and mind it, we will be given the values for Ka and CH3COOH. Will be given the values. Let's do an example. Yeah, let's do an example. Let's say the value of Ka in this case is given 1.79 into 10 to the power minus 5. The unit is mole per dm cube. And the concentration of CH2COOH is given 0.25 mole per dm cube. You can just pause the video and take it for yourself. And I'll be like giving a bit of time, but yeah, like you can try it yourself. Simply place the value of K over here and CH3COOH over here, and the square. Don't forget to do the square root, because that's one of the important part, and the students tend to like do the mistake of like forgetting to square root it. And after doing the square root, we can simply just place the value in negative pH. At first, let me write the H plus value. After calculating, we would get the value of H plus to be 2.12 into 10 to the power negative 3 mole per dm cube. And simply placing it in this, like over here, we would get the value of pH. Into the value should be somewhere around logarithm of 1.12 multiplied with the negative sign, get 2.6. So the answer should be, the pH should be 2.67. That should be the pH. So that's basically it. Now let's move on to some comparison term. Like if we get certain values, let's say in this way, let's say we have some structural formula CH2COOH. There are certain questions in the question paper, like they tend to come in this way, CH2COOH, like they tend to give you the values of pKa. Oh, okay, I forgot to mention what is pKa. So pKa is simply the negative logarithm of Ka. Ka we just saw, which is the acid dissociation constant. So that's actually, we can write in capital term or we can write in small letter a. So pKa is basically negative logarithm of Ka, the Ka value. So they will be giving us the values for Ka, and they will be mentioning for which molecules the Ka values are, pKa values are given. Sometimes they will be giving you the pK value. Sometimes they will be giving you the simple Ka values. So the pK value of this is 4.8, that is 4.9, that is 2.8, and that's 4.0. So from this 4 acid, let's say we are being asked to compare them. So the pK values from this to this and that to that, like we can like simply linearly, sequentially, we can compare each of them. and you can try to find the answer. So let me help with this equation. The If we compare the first two values, like 4.8 and 4.9, like the first acid and the second acid, why do they have a different pKa value? First, let's write the value for pKa. pKa is equals to what? Negative logarithm 10 Ka. So K is what? Ka is basically, if we simply write the equation for Ka, which was Ka is equals to H plus square divided by the acid, or yeah, well, let's say the actual acid. So we can say K is actually directly proportional to H plus, isn't it? It is directly proportional to H plus, the concentration of H plus. Plus, like, consider the equation. The H plus was in the numerator. So if H plus values increases, K value should also increase. If it decreases, it should also decrease. So that means they are directly proportional. If that's the case, then we can simply think this in terms of H plus. So if we move this on the left side, let's say consider this over here, minus pKa, simply like rearranging the equation, we should get log 10 Ka, and log 10 Ka logarithm function, when it goes on the other side, it becomes the power of the term, so negative pKa equals to Ka. Now consider that Ka equals to negative pKa. So if you simply now place each of the pKa value over here, you see as the value of pKa increases, this value decreases, and as the value of pKa decreases, this value increases. So that means if pKa value increases, Ka value decreases, and if pKa decreases, Ka value increases. And Ka, which is acid dissociation constant, if it is directly proportional to H plus, that means what? If Ka increases, the concentration of H plus also increases. Now consider over here these two terms, like these two equations, these two molecules. If we write it in simple term, or if we try to break it down, then in the first one, which is actually methanic acid, sorry, that is actually ethanic acid. So ethanic acid has a single alkyl group, which is the methyl group. But in the second acid, which is actually propanoic acid, that has two alkyl group, or we can say like that is actually ethyl group. So the greater the, or the larger the number of the alkyl group, the like the more they have the tendency to donate electron. Okay, there is this term, the alkyl group has a tendency to donate electron. So alkyl groups are actually known as what? Electron donating group. Electron donating group. So if they are electron donating group, that means they tend to donate electron, release electron. So they push electron away from them. They push electron away from them. If they push electron away from them, then they are going towards the OH, the hydroxide part. If they're going towards the hydroxide part, then what happens is actually we can write the equation. Let's say CH3 COOH is methanic acid. If it dissociates, then CH3 COO minus will be formed and H plus will be formed. Now, if more electrons are placed over here, that means what? More like oxygen has more electrons. If oxygen itself has more electrons, that means the greater the number of like electron oxygen going to have, the more electronegative O minus will be. If the if O minus is more electronegative, they will tend to attract the opposite charge more. So if methanic has like this, let's say one alkyl group, and if methanic has greater number of alkyl group, then there will be greater electron donating groups. If number of electron donating groups increases, that means the number of electrons on oxygen that will also increase. So oxygen will have more electronegative power. So CH2, 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 COO minus. this should be much more electronegative than compared to the methanoic part. That's methyl part, methyl and ethyl. So ethyl is more like it donates more electron than the methyl group. So that means that means propanoic acid has more electron donating group compared to the ethanoic acid. That means this is much more stable. Why? Because this oxygen will pull more hydrogen towards itself compared to this one. That's why the pK value of this is greater. The pK value of the pK value of the the next term, the second term. That means these terms, the pK value is increased. So if you place the higher pK value here, we see the K value decrease. And we know if K and H plus is directly proportional, K value decreases, H plus value decreases. That means the concentration of H plus is actually decreasing. Now, if we compare this over here from the equation, if this one is more stable, that means what? H plus will be staying here more, or more H plus will be here. If this one is less stable, then less H plus will be staying here. That means concentration of H plus will decrease. The equilibrium shifts to the backward direction compared to here, equilibrium moves to the forward direction. That's what it was suggesting, that it has a lower pK value. The pK value over here is lower, and over here pK value is higher. So that means pK value is inversely proportional to K. So pK value, we can also say that it is inversely proportional to H plus. The pK value increases, H plus value decreases. That means concentration of H plus decreases. So the solution becomes less acidic. But if pK value decreases, the solution becomes more acidic. Try to pause the video and try to think, and you can also like rewind the video and go on to the material again and again in order to like think it wisely, but to like think it more deeply. Let me recall the part again. Since in the second equation, the H plus was not existing in greater amount. That means in propanoic acid, in propanoic acid, there is greater number of electron donating group. If electron donating group is greater, that means H plus exists less. So if H plus exists less, then H plus's concentration decreases. H plus concentration decreases, the solution is less acidic, and vice versa. Okay. So that's the part, and that means the acidity of CH3COOH is greater than acidity of CH2CH2COOH. Let me help with another one, which is the number 2 and number 3, the equation from number 2 and number 3, which are this one is propanoic acid, and here, look here, there is a chlorine group. So there's a chlorine atom there. So inserting a chlorine atom actually reduces the pK value rapidly. And from this term, we can say if pK value decreases, H plus's value what increases. Okay, let's see in terms of the characteristic. How does that happen? Over here, if we try to focus over here, the chlorine, it is an electron gaining group. So it gains electron. Chlorine is more electronegative. Chlorine itself is electronegative. So electronegative molecular atoms do what? It pulls electron. If it pulls electron, then it pulls electron from the other nearby atoms. So see, it is also pulling electron from this oxygen. If it is pulling electron from this oxygen, the oxygen becomes what? Less electronegative. The electron on oxygen, it is also being pulled by chlorine. So oxygen becomes less electronegative. That means H plus is able to free or roam around. Why? Because there is no obstacle or no negative charge to pull it towards like itself. So H plus is free to move. compared to the normal CH3, CH2, COOH. That means here H plus is more stable. There will be more amount of H plus. So due to that chlorine, like simple chlorine group, the OH bond in COOH becomes weaker. So over here, the COOH bond becomes weaker. That's why it is like more acidic compared to this. Because H plus exists here more. And if we compare the acids of the acid number 3 and acid number 4, it is the same thing, like the molecular, the formulas are the structural formula. Sorry, their molecular formulas are same, but the structural formula are different. So this basically number 3 acid, and this is number 4. This is the chlorine, which is near to the OH group, and here the chlorine is farther away from the OH group. If that is farther away from the OH group, that means this pulling effect, the pulling effect of the electron by the chlorine is lesser here compared to here. That means if this one pulls it closer towards itself, over here, this CH, like this COOH bond is much more weaker compared to here. If that's the case, the chlorine in number 4 is less electronegative compared to number 3. So the acid in 3, it is the chlorine in acid 3, that's more electronegative compared to acid 4. That's why OH bond in number 4 becomes less weak compared to over here. That's why if that becomes less weaker, if this one, this OH becomes less weaker, that suggests that the COO minus group will be there with more electronegativity compared to over here, because chlorine is pulling electron here more strongly compared to the 4 number. So in the acid in number 4, that's going to pull less, like the chlorine there is going to pull less number of electron or less electron. As a result, this bond is less weakened. If this bond is less weakened, there will be strong attraction between COO minus and H plus. If that's the case, that means H plus will be less available, because this is in that case more electronegative. So it is going to pull more H plus because it's negative. So it's pulling positive charge towards itself. That means H plus will, the value of H plus will decrease. And if H plus value decreases, what happens? H plus is inversely proportional to pKa. We can write it pKa is inversely proportional to H plus. That means if H plus value decreases, pKa value should increase. And see, the number 3's pKa value is 2.8, and number 4's pKa value is 4. That means it makes sense. The number 1 is, number 3 is more acidic compared to number 4. So pKa value over here is less. Let's do another example. This is example number 2. So as you move down the chart, the Ka value is actually what? It is increasing. How it is increasing? See, it's 10 to the power minus 5, it's 10 to the power minus 3, it's 10 to the power minus 2. So the Ka value is increasing. Now, why is this happening? As we have learned in the previous example, the chlorine is what? Chlorine is itself electron gaining group. That means it's electronegative. Cl is electronegative. And something which is electronegative, it pulls electron towards itself. Electronegative. It pulls electron towards itself. If it pulls the electron towards itself, there is another electronegative molecule which is oxygen. So it also pulls electron from oxygen as well. Chlorine pulls oxygen from itself, pulls electrons from oxygen as well. Now here CH3COOH, there is no chlorine. That means there is no electronegative group, like except for oxygen. There is only the presence of what? electron donating group, which is this alkyl group. There are also alkyl group present. Those are also electron donating group, but the power of the chlorine molecule or the chlorine atom, the pulling power, the pulling energy of chlorine is much more stronger than the electron donating groups. So CH3COOH over here, there is the presence of electron donating group. So its electron donating group is pushing electron towards oxygen. Oxygen is becoming what? More electronegative, more negative charge is being accumulated on oxygen of the COO, like over here COO minus part. So if there is more negative charge on the oxygen, that means H plus will not be able to stay there alone for a longer period of time. Why? Because a negative charge is obviously going to attract an opposite charge. So H plus is going to combine with COO minus, forming that COOH back again. That means here H plus will be staying, like will be unstable. That means the CH3COOH is regenerated. And if we simply write the equation CH3COOH, this dissociation reaction CH3COO minus plus H plus, the equilibrium will be shifting to the backward direction, reducing the concentration of H plus. That means we already know H plus is directly proportional to Ka. Now see one thing, this is Ka, not pKa. So Ka is directly proportional to H plus, as we know from the equation. Ka is equals to what? Concentration of H plus square divided by the acid itself. So Ka is directly proportional to H plus. That means if concentration of H plus decreases, Ka value decreases. Now, if the values, like there are the terms Cl, there's the molecule, there's the atom Cl included over in of the molecule. Chlorine is electronegative, as I mentioned. So chlorine is going to pull the electron from oxygen toward itself. So that means oxygen will have less electron force. It will be less electronegative. It will be having less negative charge. If it has less amount or weaker negative charge, if the negative charge is, let's say, very small, then that means that will be less effective to hydrogen. If that's the case, hydrogen is having less prevention from like roaming around as a free ion state. That means more H plus concentration. The concentration of H plus is greater in number 2 compared to number 1. Coming to number 3, see there is two chlorine now. That means more electronegative atoms. If greater number of electronegative atoms are there, that means the pool of electron towards them will be in greater amount. If that's the case, that means oxygen will be now left with little negative charge or no charge. If that is the case, H plus is now very free to move around. Now, if H plus is there in the solution in immense amount, we can write the equation for CH3COOH. If the reverse reaction is like this, CH2COO minus plus H plus. If the H plus is in greater quantity, that means H plus concentration is greater, and we just saw H plus is due to the proportional to K. So H plus concentration is greater, K's value is going to be also greater. That's what is happening. H plus concentration increases as you move down the loop. The K value is also increasing. Also to remember, if H plus concentration increases, acidity increases. Now, we often confuse ourselves with the pKa, Ka, H plus concentration and the pH value. Let's do a short recap on the pH value. pH here is 7. So lower the pH value, higher the acidity. pH value is lower, that means acidity is higher. That means what? H plus's concentration is greater because acidity depends on H plus. If H plus's concentration is greater, that means what? The value of Ka is also greater. Now, Ka and pK is inversely proportional. That means pK value is what? Lower. So try to remember this pattern. pH. If pH is lower, that means acidity is higher. If acidity is higher, that means concentration of H plus or the amount of H plus in the solution is greater. H plus is greater, that means Ka value is greater because they are K proportional, and K and pK are inversely proportional, so pK value decreases. Opposite happens if pH value increases, acidity should decrease. Not given in the book, but it's my like normal theory. So acidity decreases, H plus it's a ratio type. So H plus value decreases concentration, and K value decreases, and pK value increases. So this is the case. Let's do our last example, which is a question has been given here. Now, don't think that these are actually two separate equations. These are like this is the same equation, but having two different stages. The first one is this is stage one, where this molecule, this dicarboxylic acid, there is this CH2N group where N is the number from 1 to 3. So this CH2 group would be, let's say, there's only one CH2 group, or there could be like two CH2 groups, or there could be three CH2, like three CH2, like this CH2, 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 and there are like carboxylic acid groups on the like those two sides. So that's why it's sort of a dicarboxylic acid. The stage one is like the first dissociation, acid dissociation reaction, where the first H plus or one of the carboxylic acid is actually dissociating, forming the H plus ion. And in the second stage, like since I didn't have like any space left here, so I rewrote the part over here. And in the stage two, this is also further dissociating, like the second group, and forming the further dissociating in the stage two. Now you have been given the values of n, like they are changing the values of n over here in the equation, and with the values of n being changed, they are also like for each values of n, like they're following up the two-stage reaction. They're given the values for pKa. So pKa in stage one and pKa in stage two. This is actually pKa1, and it was pKa2. Like in short, pKa2 representing the stage two reaction, and pKa1 representing the stage one reaction. So the pK value of stage one is this, and pK value of stage two is this. You can see pK values, like pKa1 values, are comparatively smaller or lower than the pK values too. So that's one thing to notice. Now let's get to the question. The question states that pK value of CH3COOH, which is actually ethanoic acid, is given 4.76. Now the question is, suggest why the pK values are smaller for ethanoic acid. Now they have actually asked the pK value 1. This should be actually pK value 1. Yeah. So suggest why the pK value 1, or the pK value 1, which is the stage 1 pKa values, the pK values, why are they like smaller than the values for ethanoic acid? Now coming back to here, you can see that the pK value of ethanoic acid is 4.76, and all of the pK value 1, or the pK value of stage 1, they are lower than the 4.76 mark. Now diacids are more acidic than the carboxylic acid. Let's forget about the stage 2. Let's not think that the stage 2 exists. Let's think the stage 1 only exists. If stage 1 only exists, then the thing to remember, or thing to like consider here, like there is the carboxylic acid group, there is another carbon here. So there is two carboxylic acid groups, so it's a diacid, so dicarboxylic acid. These are like stronger carboxylic acids. Why? Because of this dicarboxylic group, one of the carboxylic acid group, it acts as a electron withdrawing group. What does the withdrawing group mean? Like normally, what do we mean by withdraw? Simply, if we go to some shop and we tend to give money, like in exchange of some certain product, and we suddenly decide not to buy the money, we withdraw the money from them. We try to like take the money from them, or let's say we are withdrawing money from ATM cash book. So we take money. So we are pulling, or we are taking into us. That means over here, this withdrawing is the same thing as like we did previously for chlorine, which was an electronegative group, which was pulling electron. Same thing is going to apply here. Let's say if this is one of the carboxylic acid group and this is another, let's say this the left hand side COOH, again this could be any one, but let's consider for simplicity one of them, which is let's say left hand side one. This is the withdrawing group, which is pulling electron from every other atom. That means it is also pulling electron from that CH3COH, this OH group. This O, the oxygen, the electron from oxygen is being pulled towards the other side, like the other side's carboxylic acid group. That is leaving this O with little negative charge. If very little negative charge is on oxygen, that means H plus is able to roam around freely. It's more stable. That means acidity of it is greater. So stronger or higher concentration H plus will be there. More H plus will be in the solution, and more H plus in the solution. That means what? From this part we know, if higher H plus is in the solution, the acidity is greater, pH value is lower, Ka value is greater, pK value is lower. See, pK value is lower. So pK value is lower. Actually, it defines the pK value of CH3COOH is higher, and the pK value of, let's say, this one is lower, that one is lower, also the third one is lower. So that's answering our part A's 1 number question. Part A, second question is like suggest why pK values becomes larger as n increases. So now we have to compare in between them, like why do they increase? Thing is that like they increases because if we consider the distance between this CO2H group, the distance between one CO2H group and another CO2H group, what is happening? The distance is actually increasing, isn't it? From one carboxylic acid to another carboxylic acid. That means the pulling effect is going to be get reduced. If the pulling effect of, let's say, the electron, withdrawing effect of electron by one of the carboxylic acid decreases, what is going to happen? The oxygen on the other side will be more electronegative. The electron will be less removed or will be staying there with the oxygen more. That means it will be more negative. If oxygen is more negative, that means what? The H plus will be in prone of like in danger, that H plus is not going to exist because a negative charged atom is going to simply attract a positive charge atom and like ion. They are going to like combine together and forming a bond. So negative charge ion, sorry, I told atom, but negative charge ion. So negative charge ion and positive charge ion, they're going to simply combine together and form the compound. That means H plus, concentration of H plus will decrease. So if concentration of H plus decreases, what happens? Acidity decreases, pH value increases, Ka value decreases. That means pKa value increases. That's what is happening. The pK value of each of them, each of the terms are what? They're increasing. That's what they asked us for. Okay. I hope that's clear. If not, then like try to rewind and go through the answer again. Also, like try to make sense by yourself. And question B, there's asking us suggest why pK value 2 in the table are larger than the pK of the ethanoic acid. So C pK1, like the pK value of the ethanoic acid is what? It is 4.76, and pK value of the stage 2 reaction of each of the n values are what? They're higher than 4.76. Now see here, this like after stage 1, there is already a negative charge. If there is already a negative charge, try to think, if I am already negative charge, will I to donate or like leave a positive charge from my place? If I, let's say, if I'm having a negative charge, will I tend to like, obviously I'm going to attract positive charges towards me myself, isn't it? If I even have a positive charge on me, am I going to lose it? No, because I'm negative. I'm obviously going to try to attract it and keep it myself, keep it towards myself. That means ethanoic acid like is more acidic, or we can say at first let's think it in this way. The pK value. Okay, so the pK value are actually higher. Higher the pK value means what? Higher the pK value, lower the Ka value, lower is the H plus ion. That means acidity decreases, pH value increases. So acidity is lower, H plus is lower. Now, as I was saying, as I was mentioning, so if I don't lose that H plus, that means what? I'm going to keep the H plus onto myself. That means H plus will be in the solution. There will be less amount of H plus. So if acidity, like if H plus has a lesser concentration, that means what? Lesser acidity. So if the acidity is lesser, that means what? pK value is higher. So that's what he's saying. As there is already a negative charge in the like this molecule, already a negative charge over here. That means it has a less tendency to donate H plus, or the H to remove another H plus, since like over here we have already H plus like already donated over here. And if we want to remove another H plus, making it 2H plus, like removing all the H pluses from both the sides, like it's very difficult. So there is another term, we say that the removal of H plus from an anion, focus on the part, from an anion, removing an H plus ion from an anion is not electrostatically favorable. Not electrostatically favorable. Yeah, that's it. Thank you for today. We will see you in the next one.